Hello, my name is Kale, and I'm an assistant professor of computer science and data science at the University of Chicago. Today I'm going to share my efforts with colleagues at Northwestern and University of Washington to incorporate visual model checking into a drag-and-drop visual analytics tool. Imagine an analyst named Juan who has been contracted by a local school district to investigate factors that contribute to student absences. He pulls data from the school district into a drag-and-drop visual analytics tool and begins exploring it. He quickly discovers a possible pattern of interest. Students who study fewer hours per week are also absent more often. To Juan, this pattern is pretty convincing at first, but he wonders if it could be spurious or if it could perhaps be explained by confounding factors. In a typical visual analytics workflow, one can facet the relationship between absences and study time by other variables to deepen his understanding of this pattern. He discovers that the relationship between study time and absences seems stronger, and that absences are overall higher when student's guardian has higher levels of education. This raises even more questions for one. Does this pattern actually reflect an interaction between study time and guardian education? Or is study time even an important predictor after accounting for guardian education? Without the aid of statistical approaches that aren't supported in most visual analytics tools, it's hard to even begin to rule out or differentiate between these alternative explanations. Yet, if one doesn't scrutinize these provisional interpretations, he may not know where to turn next in his data exploration. In EVM, we investigate how a design pattern called model checking can augment data exploration workflows. Model check visualizations show discrepancies between observed data and model predictions. They provide the user with an explicit visual reference of what it would look like if some model were true. This follows from an analogy between visualization interpretation and model checking in statistical workflows, where I see some pattern in a visualization and I might fit some model to it. I might revise my visualization to show me the degree of misfit more clearly, now looking at residuals. I might compare what I'm seeing to some visual expectations that I have for what a well-fitting model should look like. How much deviation is there? This informs an appraisal of signal, akin to statistical test, but informal and often implicit in the mind of the analyst. When comparisons to a reference model are implicit, as they often are in visual analytics tools, it's easy for analysts to arrive at mistaken conclusions about the evidence that a visual pattern provides for some insight. EVM is an attempt to provide analysts with ways to externalize more of this thought process. For example, with EVM, one can express and check models representing alternative data interpretations. First is a null model, where predictions, shown in orange, show what absences would look like if they were drawn from a negative binomial model with no predictors. Second is an alternative model in green, showing how the data would look if study time was actually predictive of absences. Hypothetical outcome plots show uncertainty in prediction sets. Seeing this visualization might make one less convinced of his initial insight that study time is an important predictor, since the patterns predicted by these models don't look reliably different. One can also check models that use guardian education as an explanatory variable. First, he specifies a model in orange where only guardian education is used as a predictor, and this does a decent job of accounting for the apparent relationship between study time and absences. Second, he adds a model in green where both guardian education and study time are predictors. This model does a slightly better job of capturing the tails of the data distribution. Although he recognizes that his interpretation places a lot of importance on a handful of data points on the edges of the scatter plot, one's new operating hypothesis is that guardian education and study time are important to consider together. However, he should confirm this with new data that wasn't used to select the model. We ran a user study to evaluate how incorporating model checking into a visual exploration tool changes analysis behaviors. We recruited 12 data scientists practicing in the public and private sectors to participate in a study that was part think aloud and part semi-structured conversational interview. The study followed a pre-post design where participants analyzed two data sets. First, they used a simple visualization tool with no model checking functionality, and then with the second data set, they used EVM. We qualitatively analyzed interview recordings and transcripts, focusing on changes in analysis behaviors with versus without model checks. We found that with model checks enabled, participants exhibited less breadth of exploration and focused more on understanding the data generating process through incremental model improvements. For example, one participant described how following up on reasons for model misfit steered his thinking. With the initial Think Aloud session, I didn't think about bounds as much. I don't think it came up, but it was only when trying to describe a model that I started putting these theoretical bounds on what values could take. Many participants described a similar pivot to focusing more on things like variance, boundaries, and distributional forms. However, for a smaller subset of participants, model checking led to fixation on non-conceptual details of the analysis process. For example, one participant worried so much about model implementation details that they did not explore most of the dataset when using model checks. A couple other participants got distracted by trying to make model predictions visually match the observed data, and they eventually responded to misfit by dumping predictors into the model bar unsystematically. For another small subset of participants, model checks were often used for one-off hypothesis testing. After discovering a possible relationship, they would create a model check visualization to see whether or not a model asserting that relationship seemed plausible. When making visual inferences, users seemed to imagine a boundary around high-density regions of distributions. We dubbed this boundary the density cliff and observed that participants placed outsized importance on values past the edges of the cliff. One participant seemed particularly self-aware about this. He said, "I do see that, again, these kinds of larger fires are occurring, but that's really cherry-picking just a few high-leverage points, though, so I'm not sure that it means a whole lot." All participants were similarly cautious about treating model checks as a definitive inference method. We found this encouraging because it shows participants maintained a skeptical mindset and avoided the mistake of accepting a well-fitting model as verification of truth. Participants frequently requested diagnostic metrics to supplement their visual judgments, especially when they encountered situations where multiple models seemed to fit well. In the paper, we talk about various technical challenges of incorporating model checking into exploratory visualization tools. Here I'm going to emphasize two in particular. First is the design of model recommendations. Our work clearly motivates automated assistance when responding to model misfit. Participants tended to identify misfit based on visual cues such as asymmetry or heteroscedasticity in model residuals. Although all participants followed up on misfit when they identified it, they often did not know what incremental modeling changes would improve the apparent model fit. We proposed choosing model recommendations based on the kinds of visual cues that participants use to identify misfit. For example, enabling interactive visual selections of subsets of the data that aren't accounted for very well by the user's current model. Importantly, this means that as users explore model space by checking different models, they are providing sort of a trajectory of interpretation that recommendation systems can attempt to extrapolate or even countervail with well-fitting adversarial suggestions. We caution against model recommendations that are not proximal to the current path of exploration, since we posit that these could be distracting and potentially not very meaningful to users. A second challenge related to modeling is to provide safeguards against post hoc statistical inference. Previous work on visual analytics frames this in terms of the multiple comparisons problem, highlighting the risk that repeated statistical comparisons enabled by visualization tools might lead to a high rate of spurious insights. As a solution, we suggest that future tools like EVM should incorporate holdout sets for confirmatory inference. Users could register promising candidate models during exploration, and then they could use an entirely separate version of the dataset to support statistical inferences with guaranteed error rates. As an alternative solution for post hoc inference, some recent work explored design patterns where models can only be specified before seeing the data. This limits opportunities for p-hacking, but requires unrealistic limits on when and how frequently data can be viewed. In summary, with EVM, we contribute a proof of concept that model checking can be integrated into visual data exploration tools. We demonstrate how model checks can help to drive data exploration and explore what design patterns might be required to bring this vision to fruition.